In the class of today, inshallah, the objectives are understanding the use of three-phase transformer, know the construction of three-phase transformer, knowing the connection of three single-phase transformer bank, and recognizing the phase shift between primary and secondary. And if we still have time, we will discuss the single-phase equivalent circuit of the three-phase transformer. In the previous class, we discussed the auto transformer and we solved a small example. We will repeat the example in order to deliver to find the notes. If anybody should have opened his mic, please mute.
Doctor, could you upload this presentation in the Blackboard because it's not available now?
Which one of the auto transformer you mean?
The three-phase transformer.
Okay, after class I will do that, inshallah.
Because I'm putting the slide inside the tablet to follow you.
Right, okay. Okay, inshallah. From the next class, inshallah, it will be ready before the class. Right. For now, shabab, single phase 100 kVA transformer. So it's two winding transformer, normal transformer. And the turns ratio is 2000/200. And the apparent power rated apparent power is 100 kVA. Now, if we would like to reconnect the two winding transformer as auto transformer, as shown here in this figure. So as you can see, we have the 2000 volt winding. This is the 2000 volt winding. And this is the 200 volt winding. So if we connect the 200 volt on the top of the 2000 volt, this is going to make the voltage here 2200 volt. However, you have to consider that the dot coils are connected in this way. Otherwise, the voltage will be the difference. So now the two coils are connected like that. The low voltage is connected on the top of the high voltage one. For that, we have now 2000 voltage input and 2200 volt output. So this is now the low voltage side and this is the high voltage side. Now, the question is now, we have here this coil which was working at 100 kVA and it should work at the same value. Cannot work with higher ampere because it's designed for this value. So if you calculate the current moving in this coil based on the 100 kVA and this volt, you will find the current here is 50 ampere. And similarly, when we calculate the current moving in this coil, in the top part of the coil here, you will find that due to the 100 kVA, a current will move here of 500 ampere. However, due to this connection, you will find that 50 ampere is going to move in this coil, 500 is going to move in this coil, and applying Kirchhoff current law at point B, you will find that the input current is 550 ampere. So we calculated this in the previous class, and we could find that the apparent power that is going to be input to the transformer now equals V low multiplied by I low, which is 1100 kVA. So now the notes are, if we have single phase transformer two winding and just connect this transformer as an auto transformer, the kilovolt ampere rating will be increased. Why this happened? Actually, the two coils here, the two coils, when it was not connected, not physically connected, the rated apparent power that can be delivered is only 100 kilovolt ampere. Because the magnetic core can transfer the current due to primary, which is 50, to secondary, which is 500. So the power transferred by magnetic core is only the 100 kVA. However, due to the connection here, extra current will be moved from the supply to the secondary. In that case, the apparent power due to the connection between primary and secondary will be increased by another 1000 or 1000 kVA. So the power transferred now, شباب, are coming from two different ways. One because of the magnetic core, and another one due to the connection, the physical connection between primary and secondary. Right. Note that the higher rating of an autotransformer results from the conduction or conductive connection. Because we said due to the magnetic core only, the 100 kVA will be transferred. However, the remainder, which is 1000 kVA, will be conducted due to the connection or conductive connection. So the conclusion is not all of the 1100 kVA is transferred by electromagnetic induction. Also, note that the 200 volt winding must have sufficient insulation to withstand the 20. And if we have a look here to this winding is made for the two winding transformer to support or withstand 200 volts. However, now the coils and the insulation of the transformer is applied to 2200, which is 11 times of the rated value. If the insulation of the secondary or the 200 volt coil cannot support this volt, the insulation will be damaged and the transformer will be burned. We cannot make this connection if the 200 voltage coil is not sufficient isolated to support the 2200 volt. So not all of transformers can be connected like that. We have to check first the insulation of the transformer in order to recognize can we apply this connection or not. So for now, the advantages of the autotransformer can be lower leakage reactances. If we compared transformer with another corresponding transformer with the same rating, we have now the autotransformer of rating 11. If we compare this to a two-winding transformer with 1100 kilovolt ampere, you will find that the leakage reactances are lower in case of the autotransformer. Okay, why? Because already, if you would make the same connection, can we refer again to the example here? Now we need the secondary to be 2200. So 2200 divided by 2000, 2200 over 2000. So N1 over N2 equal 0.9. the number of terms will be different for the same for the same or equivalent two-winding transformer. So this is going to make the reactance of the equivalent two-winding transformer higher than this transformer now. Okay. Also, for the losses, يعني for this transformer, for this construction of auto transformer, you see this winding which supports 50 ampere. The impedance is different compared to the winding that should work with 550 ampere. For that, you will find that the losses, the resistance of this connection here, the copper resistance, is lower than the case of the two-winding transformer for the same rating. So we expect also to have lower existing currents and losses, lower exciting current, sorry, because the exciting current in the auto transformer now is 50 amp, and in the corresponding two-winding transformer is 550 amp. So it will decrease also the core loss. So all of losses now will be decreased. The core loss will be decreased. The copper loss will be decreased. The leakage reactances will be decreased. Also, the kilovolt ampere rating will be increased. And now you can obtain variable output voltage. So these are the advantages of this connection of auto transformer. However, the disadvantage is that you already lost the isolation between primary and secondary, which is one of the very important features of the two-winding transformer. So this is now the advantages and disadvantage of auto transformer. Any questions شباب regarding this part?
Yes, دكتور.
تفضل.
لما نسوي لهم دكتور ده it will not be magnetic anymore because they are connected to each other, right?
Not right. Now both are exist, magnetic and physical connection. For that we said the 100 kVA transformer, if you connect it as auto transformer like that, the same 100 kVA will be connected by induction, by magnetic. Because if you have a look again here to the circuit, there is already a primary current in this coil. Is it right or not?
Yes.
Which is 50 amp. So if we connect or we did not connect, the 50 ampere is here, and there will be an interaction between these two coils. Okay. So because you do not change the two-winding transformer in terms of the transformer wound or anything, the magnetic core and the windings are the same. You just make extra connection. So the part of magnetic power will be transferred, which is 100 kVA. However, due to the physical connection, you will have extra power. So now you conducted two different powers as we agreed here. The 1100 composed of 100 coming from induction or call it through magnetic transfer, and the remainder will be due to conductive connection. Okay? Is it clear now?
Yes, Doctor.
Okay. Right. Any other questions, Shabab, regarding this part? Okay. Start in three-phase transformer. Firstly, why we need a three-phase transformer? Now we have single-phase transformer. Why we should use three-phase? In our power grids, in generation, in transmission, and distribution. All of networks are consists of three-phase networks. So, in order to equip transformer with these networks, you need to use three-phase transformer. And actually, three-phase transformers or three-phase in general used with high power applications for any kind of loads. And if you have a small air condition, for instance, at home, you will supply it only by single phase. Okay. However, if you have central air condition, for instance, a machine of 10 kVA, so in this case, you cannot take single phase 10 kVA from your home. And it's not safe for the wiring inside your home. So it's better to use three-phase in this case. So we prefer three-phase all of time for the matter of high power. So for high power, three-phase are used in power generation, in power transmission, and distribution. And similarly, the transformer which is used should be also three-phase transformer. Right. So three-phase system is used to generate and transmit bulk electrical energy. Bulk means high power. Three-phase transformers are required to step up or step down voltages in the various stages of power transmission. We discussed before that at the generation stage, most of generators operate the rated voltage around 10 kilovolt to 20 kilovolt for instance. So this volt cannot be transmitted through long distances. We discussed this in the first class of transformer because of the problems of power loss and long distance. The voltage drop and power loss on the transmission will dissipate all of the transmission energy. So we have to use a step-up transformer at the beginning of transmission, say stepping up from 20 kilovolt to 500 kilovolt. And after transmitting this power at the receiving end, we should step down the voltage again. However, we step down the voltage in many steps, not in one step like in the beginning, like the stepping up, because we need to distribute this power among industrial loads and domestic loads. Industrial loads may need relatively high voltage, maybe 12 kilovolt for instance, and after that, the distribution to transformers which are very close to your home, you will find these transformers around 6 kilovolt to 0.4 kilovolt. So we step down the voltage in many steps according the loads that we are going to connect through substations and distribution transformers that are exist close to your homes. Right. Three-phase transformer can built in one or two ways. Can be built in one or two ways. One of two ways, sorry. What are these two ways? First is by suitably connecting a bank of three single-phase transformers. Simply, you can bring three single-phase transformers and start connecting these three transformers, either star or delta or mix between primary and secondary, in order to construct a three-phase transformer. This is one way. The other way is to create or manufacture a magnetic core for the three phases of power. So either making three single-phase transformer or making one common core for three-phase transformer. These are the two methods used in manufacturing three-phase transformer. One of the advantages of three single-phase transformer, or we call it transformer bank, one of the advantages is if one phase has any problem, which means one transformer has problem, one of the three, you can remove it completely and stay connecting the three-phase systems. However, you will transmit partial transmission of the power, not all of the power. This is called V connection or open-end connection, and we will describe it later. Okay. So, in terms of maintenance, three single-phase transformers will be better. However, in terms of performance as a power transmission and efficiency, the three single phase has lower performance compared to the use of one complete core for the three phases. For that, most of power stations transformers at the transmission systems using three-phase transformer based on one magnetic core, not three cores. A set of three similar single-phase transformer may be connected to form three-phase transformer. And here, this is just a note that the three transformers have to be similar, identical power and voltage levels. But this is going to make transformer as balanced three-phase, because if it is not similar phases, you will have different impedance per phase, and this is going to make imbalance in the connected load. Right. What about the connection of these transformers? We have two connections, or two well-known connections for three phases, which are star or Y connection and delta connection. So we can connect primary or secondary, whatever the needed application. We are going to describe the four different connections now, and we will see the different applications or different needs for these configurations. So we can connect either star or delta connection. So what are the four connections? The four connections, as you can see here: Y delta, delta Y, delta delta, Y Y. طبعا يعني Y delta means primary is Y and secondary is delta. Okay, so first is the primary connection and the second one is the secondary winding connection. Okay, let's see here the first connection, which is Y delta. As you can see, how we can connect the three-phase or the three single-phase transformers to construct Y delta. Simply, as you can see here, these are the three coils of primary. So طبعا يعني it has to be similar coils and similar voltage ratings. Okay, and you cannot switch between step up and step down in the same transformer. يعني all windings should be the primary windings, and all the other three windings should be secondary. So we have three identical coils here. How to connect, to construct a Y connection? Simply, you have to connect like that way. If you start here with the dot, then coil, so the end here should be the same, away with the dot for the three phases. Otherwise, it will make a problem in the magnetic transfer. So this is now the connection of star. Simply, the same for delta. Can you see? Here we started with dot, end with coil. So the second coil or the second phase should start with dot and ends by coil. Third phase starts by dot and ends by coil. So this is the sequence of the connection. Regarding the voltage and the current levels now, we first would like to refer to a very important thing. Yani if this is phase A and this is phase A, so this is primary and secondary for the single phase transformer, you know that the power will be transferred and the voltage will respect the ratio between number of turns here and number of turns in the secondary. So this volt divide that volt equals N1 divide N2. Take care about the voltage now, because the voltage applied to this coil is not the same like before because of the Y connection. Yani, the voltage here applied, which is the line-to-line volt, for a star connection, you will find the line to neutral volt is line-to-line over the square root of 3. So you can apply the transformer turns ratio only on phases. So the phase volt here, V over square root of 3, will be transmitted to the other side, okay, and divide by the turns ratio. So the voltage here on this phase will be V over square root of 3 over turns ratio. So this will be the voltage of this phase. And due to the connection here is delta, the coupling volt or line-to-line volt will be the same as the phase volt. So as a comparison now between the applied line voltage here and there, the applied line voltage here is V. However, here we get the effective V over square root of 3 besides the turns ratio. And if we assume unity turns ratio and you applied here V, you will find the volt in the other side V over square root of 3. This is due to star delta connection like that. Right. Regarding the current, if you measure the line current here, which is the same as the phase current, so the phase current also will be transferred and respecting turns ratio. So if the phase current here is I, the phase current here will be turns ratio multiplied by I. However, this is not the output current, it's just the phase current. So for delta connection, the line current equals square root of 3 multiplied by phase current. So this is now the line current. So as you can see, I became square root of 3 multiplied by AI. Right. What are the main applications for this connection, star delta? This connection is commonly used to step down a high voltage to a lower voltage. So this is mainly used for step down. Okay. طبعا يعني as you can see here, because also the ratio of square root of 3, so it's better to use it for step down. The neutral points of the high voltage side can be grounded, and this is very important for the protection issue. And in order to find any fault or any unbalance in the transformer, we measure the current which is moving between neutral point, and this can detect the different faults. So for a star connection, we have to connect the star point to the neutral point to ground. Second connection here is delta star, and contrary to the star delta, this one is preferred for step up. So stepping up transformer, we should use delta star connections. Let's compare the voltage and the current levels here for this transformer. If we applied certain voltage V here as coupling volt, as you can see, because the delta connection here, the phase and line voltages are the same. So the value of V will be transferred by induction to that phase, with respecting the turns ratio, so the voltage here will be V over A. However, this is not the coupling voltage. Coupling voltage here is the line to line of star. So the resultant voltage here will be square root of 3 multiplied by the phase volt. Also for the current, if you have line current I here, the phase current of delta will be I divided square root of 3, and this is going to be transferred here by induction with respecting to the turns ratio. So the current which is moving here equal I over square root of 3 multiplied by the turns ratio. And this is the same as the line current for the star. Okay, Shabab? Is it clear? Is there any problem regarding the two connections? Okay, good. The third connection, which is delta connection. Regarding the benefits of this connection has the advantage that one transformer can be removed for repair. As we discussed before, if we construct the transformer based on 3 single-phase transformers, and we have a problem in one of the transformers, we can remove it, and we will not shut down the transformer. We will keep it working, but we have to take care that the apparent power will be reduced. Will be reduced to 58 of its rated value. So this is due to the one open phase. So one open phase is called V connection, because if you have this winding, for instance, not connected, so the connection will be like V, or we call it open delta. Okay, so this is possible and can transfer 58 of the rated power. The last connection, which is YY connection, it's rarely used because you have two neutral points, and it's extra for the protection. We don't need to add two primary and secondary earth leakage. One is sufficient, in particular for small loads. Also, it has a problem with the disturbance due to nonlinear loads. If there is any disturbance in one side, it will be reflected to other side. It's not like the star delta, even for the harmonics. If you have harmonic here in this side, it will appear in the same way in the other side. However, if we consider delta connection, for instance, here in delta star, if you have third harmonic moving here in these coils, it will not appear in the delta connection. It will be circulating here in the phases and will not move on the output lines. So, delta star or star delta are preferred as connections compared to star-star connection. Regarding the voltage levels, as you can see, because of symmetry, you will have the same voltage levels, طبعا with respecting to the turns ratio, which means if this is V, the output will be V over A, without any other factor. Okay? If this current is I, the current here will be I multiplied by turns ratio. This is because of symmetry between the coils. So this is for the different connections of three-phase transformer. There is one important note for transformers, and it's useful in some application. This is called phase shift. Now, if we considered different connection for primary and secondary, if it is a star delta or delta star transformer, you will find this phase shift. However, for symmetry, the phase shift is 0. For delta delta or a star star transformer, the phase shift will be 0. Why? Let's analyze this performance now to recognize why we have phase shift. If you now supply a Y connected transformer, primary like that, with applied voltage here, VAB, and the phase voltage is VAN. Now, if you have a look to the phasor diagram, as you can see, this is VAN, and VAB can be obtained as VAN minus VBN. This is minus VBN, and VAB is this vector. So we have now a phase shift of 30 degrees between VAN and VBN. Again, let's go to the basics of transformer. Which value of volt should be transferred with respecting turns ratio, phase or line? ها شباب, we discussed it this class. Which volt will be? Sorry?
Phase.
Phase, right. So because the phase transferred by the inductor, by the induction of the magnetic core. So we should respect the phase one. So VAN here will be appeared here with the turns ratio. So VAN phase here will appear here in VA, which is the same as VAB, but by dividing by VA turns ratio. So in terms of the vectors, you will find VAN and VA of the delta connection in phase. There is no phase shift between them. Okay, so as you can see, VAN is here. This is for the star one, and for the delta one, VA or VAB is in phase with VAN. Is it right? However, comparing to the line voltage applied to the primary winding, which is VAB here for instance, VAB. So VAB of the primary winding at this angle, and VAB in the second winding is at that angle. So there is phase shift between input and output voltage. Okay, شباب, is it clear? So you'll find 30 degrees phase shift between the primary and the secondary coupling voltage is star delta or delta star. So if the connection is different, okay. However, for delta delta or star star connection, the transformer will be the same. We still have time to discuss this part. However, I believe we will need to review in the next class as well. Single phase equivalent circuits. In order to solve problems, شباب, we need to simplify the transformer. We are not going to solve the single phase, the three phase circuit. We discussed the equivalent circuit of single phase transformer, and we could see that the exact equivalent circuit is complex a bit to be applied with or be solved or analyzed with circuit analysis. For that, we made some approximation. Now you can imagine if the circuit is three phase, not single phase, it will be more complex. So we have to find something else to simplify the analysis or circuit analysis we are going to apply on the three-phase transformer. So the best way is to make single-phase equivalent circuit. It's like you converted the transformer from three-phase to single-phase and start make any circuit analysis as you made before with single-phase transformer. But this needs some conditions. First, in order to apply the single-phase equivalent circuit, all of windings should be star. All of windings should be star. Type. What if we have delta connection? If you have delta connection, so you have to make delta star transformation virtually in order to apply the single-phase equivalent circuit. For instance, we have now a transformer like that, star delta, and this star delta transformer is supplying a certain delta connected load like that. If you would like to convert to single line diagram, primary is the star, no problem with the primary now. The problem now is in secondary and load. We need to convert from delta to Y. If you need to convert from delta to Y, you have to know how you can convert delta to star. For any impedance, the impedance of delta will be divided by 3 to get the equivalent star. Okay. Right. What about the voltage of the transformer? Let's see here the transformation here to be more clear. And if this is a primary, we said there is no problem for primary. This is V and this is V over square root of 3. It's written here, it's clear. However, here from the other side, you know that the voltage should appear here, which is the phase, is a function of that volt here, who is considering Turner's ratio. So it should be V over square root of 3 divided by A. So the voltage here, V over square root of 3 divided by A. This is the voltage here. If we need to convert this to delta connection, as you can see, the voltage here is the same. This is the physical voltage. However, the voltage on the phase itself here will be different. Why? Why it will be different? Because we're now making virtual connection. It's not the right connection. So the virtual connection here says this volt should be 1 over square root of 3 of the line volt. And this is the actual line volt. So the phase volt now should be V divided 3A. Okay, شباب? Is it clear? Regarding the current, for the star connection here in the primary, if it is I, you know the equivalent of delta will be square root of 3 multiplied by Turner's ratio multiplied by I. So this is the same line current. Okay, and here it will be the same like the phase voltage for the equivalent star. Okay, so this is now the transformation made. And for load, it should be Z divided 3. So we can now simplify this circuit because all of the circuit connections are star. We can now make the connection as single phase. So for the single phase now, we have the phase voltage here, which is V divided square root of 3, here, V over square root of 3. The phase voltage here is V divided 3A, so it should be respected here, V divided 3A. And the current here will be square root of 3 multiplied by AI. In this case, شباب, if you divide the voltage here over the voltage there, you will find that the Turner's ratio became N1 divide or over N2 divided square root of 3. It's not like before. Why this? This is only because of the virtual connection. It's not right connection. For that, we can say now that we have A prime, which is the equivalent Turner's ratio. It's not the exact Turner's ratio. A prime equal to V divided square root of 3 over V divided 3A. The resultant will be square root of 3 multiplied by the Turner's ratio. So this is now the equivalent Turner's ratio that can be used. Okay. Inshallah, by the next class we will refer to this part again and start solving problems. Is there any question, Shabab, regarding these topics? Any question?
Doctor,
تفضل.
I have a question regarding the last quiz.